let me give you guys a little bit of background about me and how we got into Checkpoint. So when I was doing my postdoc at UC Davis, this was some years ago, we did a collaboration with the American Museum of Natural History in New York. And in that collaboration, we developed a software tool called IDAV Landmark, IDAV Landmark. That was a free tool that we provided through the university to the community, mainly the paleontology community, for collecting 3D points and on 3D specimen surfaces, that kind of thing. And when I left the university, I founded Stratovan, and one of the first things we wanted to do was to build effectively a better version of that landmark editor software. And that's what Checkpoint is. So Checkpoint started out as a better version to that software that could be maintained and perpetuated through time. And that was sort of the genesis of it. From a company perspective, what we're interested in doing, or have been interested in doing with Checkpoint, is taking the capability of 3D shape analysis, landmark placement, landmark-based techniques, statistical shape analysis, even geometric morphometrics, all of that into healthcare. That was a big push. We wanted to bring these capabilities into healthcare to improve medical treatment, healthcare, worldwide through this kind of capability. And that's been a long road, and it's slowly taking hold, but it's challenging for people to use the software and to know how to apply the techniques to do the assessments that they need to do. So part of this webinar is to go over some of the basic capabilities of the software, how to work with different types of data, how to place points on surfaces and objects or things, and do the data collection that you need. Please ask questions during and interrupt if you want. I'm okay with that. And we have some basic questions that the group of you provided beforehand that we're going to try to work through a bit. And I think that there's 2 or 3 questions that cover allow us to cover a wide range of things. So one of the first questions that we have is, what if you have a specimen with multiple other specimen inside of it? So if you have a CT scan or a micro CT with a bunch of little things inside, how can you pull out those individual items? And so actually, I don't recall which particular user provided the data for this, but that's what we're going to load up one of their scans and show how to do that. So the first step in doing that is you want to click on this image stack button over here on the upper right hand side, and this provides a way to load in the individual slices from the micro CT scan to create a 3-dimensional volume. The original files were provided here in PNG format, and I was able to convert those to TIFF. TIFF works better for a variety of reasons for this kind of thing. And so here you can see the individual slices going through the specimen. And what you want to do is you want to select all of these. So I'm clicking in the upper left here. And if I go too fast, just like send a message and someone will tell me to slow down. I'll try to slow down. So I've selected all of the images here. I held down Shift and clicked that so you can see them all down here. And I'm going to click Open. And now they're all listed here. It does the sorting based upon the file name. So if that doesn't work right, you can actually change the order with these buttons. You would select this one here, move it up and down. You can give it a name. So these are some kind of shell inside. An important part to keep in mind is the spacing. I actually don't know the spacing for this. It wasn't provided to us. Tonya, do you know if the person that provided this is on the webinar that can possibly provide us the spacing? Wait for a second, see if we get a message or something with the correct spacing. But you want to do the width and the height in the slice planes. That needs to be specified here. Then also the slice spacing in the Z direction needs to be provided. I don't think we have that information. So I'm just going to go with 1 millimeter spacing in all directions. And then there's several different outputs that you can do here. So one is you can output just a checkpoint file. So the checkpoint file is a text file that lives near the data files. Sorry, I think we did. I just got the. Okay, it looks like it's. Okay, here's the spacing here. So it looks like it's 0.056 millimeters in all directions. So we're going to put that in here. And then this is used for scaling the coordinate frame properly once we load the data. So the different output files are, one, you can just do a checkpoint file, and then the checkpoint file would go next to where the TIFF images are. And then when you go to load the file, the next time you would actually load the checkpoint file, which then has a reference to the image files. You could do it that way. Another option is to output a NIFTY file. So this is in the .nii format. And here you can, we have the ability to do downsampling. So the full resolution of this is rather large. So it's 1500 by 1500 by 900 slices. And that comes out to almost 4 gigabytes, which is rather large. And then you can choose these downsampling options here to make smaller versions of the data. The only issue with that is you lose resolution and quality of the image if you do that. I actually tested this yesterday, so I know it works, but I'm going to give the high resolution a try for today. And so once you pick the resolution that you want, you click Save Stack. And what it's doing right now during this process is it's loading each of those images into memory. It's building a full 3-dimensional volume into the NIFTY format, and then it'll allow us to save that out. So we got to give it a second. It's a good time to have a coffee. Hopefully everybody got their coffee this morning. This is probably the best reason I've had to clean my desk in probably a very long time. So special treat to everybody to see my clean desk. If you've had phone calls with me before, you know that my desk is not normally this clean. So we wait a little bit. Almost there. And then when it's done, it's going to pop up a little box and give you some metrics about the data values. So the values range from this to that, mean value of such and such, and that just kind of gives you an idea of the density values within this micro CT scans. Micro CT scans don't often have the units calibrated properly, so you got to be careful of that, like the density units. Should pop up soon. There we go. So min value of -32,768, max of that. Mean value some negative density value, which seems strange, but it is what it is. So click OK. Now it's going to give me the option to save. So I'm going to save it here. So Shell's NIFTY. And it's a big file, so it takes a little while. Okay, should be done now. So now if I update my folder, it pops up here. So Here we go. So here's the file I just created. So I'm going to click open here. This again takes a little while since it's a large file, but we're almost there. Once we get it in here, things will speed up a little bit. I'm going to try to keep track of the questions. So I'm not going to be very good at this. It's my first time doing a webinar type thing.
Hey, David, can you hear me? Hey, so Candace Small is asking a question about saying that they've never worked with micro CT. They've just kind of gotten started, and they're asking, do the scans need to be reconstructed before use in the program, or is what you're working on raw data? So yeah, go ahead.
Yeah, so they do need to go through the reconstruction process beforehand. So the micro CT puts your specimen in the device. It collects the projections. That's the raw like projection or sinogram data that you get out of the scan, and then it needs to go through a reconstruction process. Typically, the vendor of the scanner provides reconstruction software to do the 3D reconstruction. They do the reconstruction in the slice planes, and that's why we end up with 1,000 TIFF images, is because they're reconstructing each of those slice planes individually. And then that's typically the output from a micro CT scanner. And then that would be the input that comes into Checkpoint, is that fully 3D reconstructed scan. So it should be loading up. Almost there. So this is a big scan, so it doesn't normally go this slow. So again, this is about a 4 GB scan. So we got to give it a little bit of time. It's coming. I can see the histogram coming.
While we're waiting for it to load, Chris Robinson is posing the question: what is the maximum size of files that can be used now in Checkpoint? He's saying from what he recalls, when he first started using it, it was recommended that we click on the 3rd largest file.
Yeah. So I've never loaded one this big until yesterday. So, but it seems to work. You can see it there. So this is literally 1500 by 900 0.6 millimeter space, 0.56 spacing. It's rounded up down here, and you can see that it's got it loaded. So this is certainly the biggest file I've ever loaded into this. So let me go over just some basic visualization or just the basic capabilities. So you've got a set of tabs on the left-hand side here. So specimen is where you go to load your specimen. And volume is the main volume rendering portion. So this is doing a volumetric rendering through the data. You have the slice views. So you have the 3 slice views: axial, coronal, and sagittal over here along the left-hand side. If you click these buttons, you can move them back and forth. So if you want the coronal bigger, you can do that, and it moves it back into place. You can also double-click in the view. So if you don't, I'm double-clicking here. You can also see what I'm doing with my mouse by this little icon down here. So if I click my left mouse button, I get that button, right, middle button. If I do the mouse wheel, you can see the little blue indicator there. Sometimes I hold down keys, and you can see which keys I'm holding down here to do things. So if you're ever wondering what I'm clicking to make something happen, you can sort of, take a look at that. So you have the basic slice views. You got the 3D visualization here. It has a histogram of the data. So this is micro CT, so it's like the values aren't calibrated to anything. So if you do a medical CT scan, you'll get a calibration. Typically in medical CT, errors at -1,000. Water is right around 0, and then bone is say at like 200 or so, and then like really dense bone. Cancellous bone is much higher than that. So in this case with micro CT, the density values aren't calibrated to anything, so we get really strange values. So these are like negative whatever to some really high positive number. But nonetheless, Checkpoint's able to work with it in this case. So some other views you have a surface view, and what this is doing is it's extracting what's called an isosurface from the three-dimensional data, and then converting that isosurface into a triangle mesh. And so these are actually individual triangles where if you zoom into these and look at them, you can sort of see the facets of the triangles that are in there. And then in the slice views, you can see the intersection of the triangle mesh with the volume. And so this red line represents where the isosurface came from. An isosurface is effectively the surface in 3D that represents a specific density value. So if you think of a contour map, a topography map of height, and you have the contour lines, those contour lines are an iso line at a particular height, and that's what this is represented in 3D. And so in 3D, instead of a line, you have a surface. And so that's where we get the triangle surface from here. And so this surface represents the exact same density value throughout the volume. That density value in this case is minus 512 because it's micro CT. It's a strange value. And then you can change. If I hold down Control and I click, I can extract a different surface. So in this case, it's a little bit noisy out here, but it looks fine for these guys. So what we'll end up doing throughout the rest of the webinar is going through some of these other tabs, but like this tab is going to show our landmark points, and we have some templates that we can do, and then there's some exporting that we can do. So I'm going to go back to the volume view and cover some more of the basic steps here. So brightness and contrast, what I'm doing is I'm left clicking, moving up and down, and then you can go left and right. And what it's doing is changing these numbers that are called width and level. These terms come from the medical imaging side of things, where width and level are equivalent to brightness and contrast. And so you got to sort of play with these to get something that renders your data the way that makes sense to you or makes sense for the data. So you want to move these up and down and left and right until it looks good. And because the density values change for stuff like micro CT, it may be different for each one. However, if you have a bunch of scans that are, you're loading for your data, you can actually set default values. So in this case, I have a view, and I can do set default value, and I can put values in here. So I could say look at the width and level here, so 3884, 1127, and then I could put those values in here so that the next scan that I load uses those values as the default. So that's a way to get the rendering to match what you need to do. So for this particular data sample, the person that has this wanted to extract each of these shells individually. So they did a micro CT of a whole bunch of them. Let me change the rendering here, so we can see how they scanned them. So they did this is the outer shell of the micro CT scanner itself. That's the turntable of the scanner. And then it looks like they made a little pod or something that they put the shells into. So there's multiple specimens being scanned simultaneously. So the first task that we want to do is how do we pull these out individually? So what I like to do is I like to use these pointers. So the crosshairs here, as I move the crosshairs around, all the other slice views align to that point. So if I want to pull this particular specimen out of this sample, out of this scan, I can center the crosshairs on it, and then I can double check it in each of the views or each of the different slice views. So I've got it basically centered there. And then I'm going to click this button up here at the top. This button up here at the top turns on cropping. And what that's going to do is in each of the slice views, of course I turn it on, you can't see it, so you got to zoom back out. What it did is it turned on these blue lines. So if I turn it off, they're gone. If I turn it on, these blue lines come in. And so what I can do now is I can grab these blue lines and bring them over. And you can see what happens when I move that blue line. It crops the data. So I can grab each of these, bring it in. Then you want to look at the different views. Basically, you need to go to 2 of the 3 views to do this. And if you want to make this tightly cropped, you can zoom in and then bring it in as close as you can. Probably want to get rid of these little tubes that are around the specimen. And you want to check it in all 3 views. And then once you think you're done, you actually want to scroll through. So I'm going to scroll through and I can see that I brought this in a little too much here. So I'm going to bring this edge back out. That looks okay there. I'm going to go to this view, the same thing. I want to go through a couple of these views to make sure that you're not getting it too close or cutting off any of the specimen. So that looks pretty good there. And so that's the sub-region within this volume that I want to export. So to do that, you go to the Export tab. So Export tab, and there's the little region that I can export. And so that's within the cropped region. And it looks like we got a little bit too much here. So let's go back. Let's see where that's coming from. Way up here. Yeah, so we bring this in here. Go back and check the view. Oh, yeah, there's still some. No, it looked like too much. Oh, it was right before. Okay, so that looks okay. Okay, so let's go back to export. Export here. Looks okay there. And so there's 3 types of export we can do. So we can do volume exporting, so that'll be the 3-dimensional volumetric data. We can do surface-based exporting. So this would just be the triangle surface, and then soon we'll have some landmark points, then we can export the landmark points there. So to do this one, you just click on export volume and give it a name. And it exports just that little volume. Export completed. Do you want to load the volume? Yes. Let's load it. And now I've got that little subregion here. I can do the change the brightness and contrast. I can extract the surface, do all the same capabilities. So on the export tab, so one point of clarification, whether or not I export the cropped region depends on whether or not this button is clicked. So if I have the cropping turned on, then it only exports the cropped region. If I have it turned off, then it exports the entire region. I'm actually going to export 2 of these shells here, so that later on I can actually use them for a couple other activities. So let's pick another one here. Let's go over and get let's get this one. This looks interesting. So I had to expand the cropping region and then bring it back in on this new specimen. Scroll through, make sure it's not missing any pieces. Looks okay there. Okay, let's export that one as well. Looks okay there. Let's call this one B. So now we've got these two subregions exported individually down here. This one's interesting looking. I think this will work for what I want to do later. Later on, what I'm going to do, I'm going to try and take these two, put landmark points on them, and do some three-dimensional warping between them. See if we can get that to work. So that's how you pull out individual specimens. So I believe that answers our first question on that was posed to us. You should be able to do this, a little bit tedious, but you should be able to go through each of your specimen and pull them out individually into little subregions. And then this is still at the resolution of the micro CT. So with specimen like this, I wouldn't recommend downsampling the original micro CT because the specimen are so small relative to that original scan that if you downsample the full scan, by the time you pull out your individual specimen, you're going to lose surface detail and that kind of thing. So by keeping it at the full resolution, when you pull out the subregion like in this view here, you still are able to maintain all the detail of the individual specimen, which you can see here as we sort of scroll through it. It's quite a bit in these guys. This one in particular. I would love to know like what all of this stuff is. I have no idea what these things are. That's one of the things that's really cool about everybody that uses Checkpoint. You guys all work on different things. And I've never seen a shell until yesterday like this. Some people work on dolphins, some people work on spiders, you know, monkeys, all kinds of things. It's really fun to work with you all. Just to see the neat things that people are using this for. So one of our next questions, let's move on to the next question. Unless a particular person that provided this data has any more questions in relation to this, I'll try to keep an eye on the chat or have one of the people on my team, like Ryan or Tonya, at least holler out at me if I miss something. Someone's saying there, can you, Ryan or Doug, can you guys just talk so I don't have to find the thing if we have more questions?
Yeah, you want another question?
Yeah.
Okay, perfect. Let me see here. I just want to go back and make sure. We talked about Chris Robinson's question regarding file size. We have another question. Someone's saying they experimented a little, and in the export surface menu, you have got the option of splitting the surface into parts. That seemed to work too.
Oh yeah.
But I could not handle the volumes this way.
Oh yeah. Let me go back and do that. That's a good point. So let's turn this off. So I'm turning off the crop. I forgot about that. So in this view, so first thing I'm going to do, so because all these little bits and pieces, that's going to slow things down. Yeah. We can try it with this. So if I click on this button here, split surface into parts, it's going to try to identify each of these individual components. Trying to think of how to describe this. So if the ISO surface that was extracted for this represents a single density value throughout your specimen, if the surface, you know, connects and touches all of the different parts, then you're going to get one single triangle mesh for that object. Because each of these shells were compartmentalized in the scanning process, they're not touching. And so if you click this button, we should be able to divide all of those components into individual surfaces that can be extracted. Hopefully this doesn't crash my computer. Let's see what happens here. So if you click split into parts, so it's all of those little bits and pieces that you saw, it's also going to try and separate those out. Might have been a bad idea. The more parts you have, the longer it takes. Yeah?
I was going to say, while we're waiting for it to load, somebody's asking if have we tried Checkpoint with a Wacom tablet, an interactive pen, or only the mouse?
I believe you can use it with the tablet. I mean, the tablet mimics all of the mouse controls. So, I mean, you should be able to use it for that. I think it can often be cumbersome to use tools like that as opposed to just using a mouse. It's really hard to beat a mouse. That's like why virtual reality and augmented reality hasn't really taken off, because it's really cool to put those things on. And for like 5 minutes, it's amazing. But when it comes down to doing work, it's really hard to beat a mouse. So try to keep that in mind. Ultimately, you got to just try it out and see if it works for you and whatever your workflow is. And if you're trying to do thousands of specimens, you got to find the right tool to make you faster. So now it's split this into multiple components, and you can click through these. These are sorted based upon the size of the component. So up here we have large things, down here we have little tiny things, which I don't even know where that is. It's so small. It's some really small thing. So the larger things are at the top, and then you can, using the arrow keys to move down this list. And so here I can identify each of the individual specimen and then export that specimen. So if I want to just pop that one out, and then it's going to do it in a different file format. In this case, it's one of the surface-based formats that we support. So we'll do PLY in this case. We can load that one. Back here. Oh, we lost it. Oh, no, it's still here. Yeah, sorry, I had the wrong one. Okay, so great, we did not lose it. Here's another one. So export surface. Back to our specimen. So this is a way to do it too, but you just got to decide if you need the volumetric data, then you want to do this kind of export over here. If you just need the surface data, then this might work a little bit better. You can also do the reflected surface if you click on that, which might be useful for something. Okay, so now we've got a bunch of different shells down here. This is maybe not the best ISO surface, right? Because you have some holes there. So this is where you may want to do the surface. So if you do the surface, volumetric export, you get the raw volumetric data, and then you can change the surface that's extracted on that specimen, on that new specimen. So if I want to, so I'll show you here. So if I move this up in the density, then that gets rid of that noise there. But also you see the surface shrink a little bit. If we go down here, this is telling me that I have a bunch of surfaces extracted over here. The reason that little message pops up, because if you click all of these, if you have multiple surfaces stored in here, the checkpoint file remembers that you have, in this case, 3 surfaces stored. And so when you close down checkpoint and load it up again, it will then go and re-extract all 3 of those surfaces. The reason it does that is when you're placing landmark points onto your specimen, the landmark points are placed with respect to a particular surface. And so you're putting them onto a surface. So it tries to remember which surfaces you have selected and which ones you're using, so that it can match those up to the landmark points that you placed on there. So I'm going to get rid of these 2. I'll try this guy here. So look at this one. This one picks some weird value. So let's pick another value down here. One thing you may want to do is use the same value across your specimen. So in this case, I used 92 for my ISO value. In this case, this is minus 327. So I'm going to close that. I'm going to go up to 92 or as near as I can. And the reason you want to do that is because as you change that ISO value, because it's a density value with respect to your volumetric data. So remember the topography example of the height, of mountains and that kind of thing. If you're changing that value, you're changing literally the height value within that function. And so as you move the height up and down, that's going to change how those lines kind of circumnavigate that mountain. That makes sense. And so if you go down, it's going to get bigger. If you go up, it's going to get smaller. And that's what's happening. That's what's happening here. So if I move the value up, it shrinks the surface a little bit, and if I move it down, it expands it a little bit. And that's kind of also related to the gradient of the density value for the object that you're investigating, if you think of it that way. So I recommend trying to use a similar value across all of your specimen as much as you can. So, okay, so let's do a couple other things here. Let's look at some of the other questions. So one of the other questions was, how do you change the order of landmark points? So specifically, the question is, if I have landmark points 1, 2, 3, 4, 5, how do I reverse the order of those points? So I'll just do an example really quick for that. So we've got landmark points picked up here, and so I'm holding down Shift, and I'm going to place those points on the surface. So I've got 5 points here, and to change the order of them, I want to go switch to the landmarks tab, and I've got the points here. It may not be very clear, so if I click on the first point there, so the point 1 is the default name that's provided, that check 1 provides. And if I move that around, sort of that name changes. But you can see this value over here, 1, stays the same. So this is like our internal indexing for the point, and then the point 1, 2, 3, 4 is kind of a default name assigned to it. So I'm gonna rename these just to make it a little bit clearer. A, B, C, D, E. And now if I move this point down, you can see that I'm changing the order of that. So if I wanted to reverse the points, I could just do this. A, B, C, D, E. So that's how you would reverse the points there. So that should answer that second question. So I'm actually gonna delete these. Let me go back and show some of the basic landmarking capabilities that we have. So this is not a bad specimen to try these on. So these are the basic landmarking capabilities that we have up here. We have single point primitives, and so single point, this is very much the same as the microscribe concept back there, where you have your specimen and you can place individual points across your specimen and then work with these points. So once it's there, you can click on it, move it around. You can look at where that point lies on the surface. This is where volumetric data can be more helpful, because if I have a scan like this and I'm placing points on my surface here, I can go into the volumetric data and I can see maybe more precisely where that point lies on that surface, for example. So depending upon where you set your brightness and contrast, I can also change, how the point. So here I moved it off the surface, so it's out, hanging out in space here. So if I look at it from 3D, it's off in space. I can grab it, so I'm going to grab it and I can select it. I can't drag it around because there's no surface behind or underneath the mouse position, if you think of that. So I'm going to move it here. If I grab it here and then start moving it, it snaps back to the surface. So that's single points. You can also do a curve. So let's say we want to put a curve along here. Click that. We can just do this. 3. So I did 3 control points. in this direction. And then you can see there's these little blue points that are made in between here. So if I grab these points and move them around, so these points with the arrows are the control points for the curve. So it makes a Bezier curve through the control points, and then it automatically generates. So the Bezier curve is shown by this little red line here, and then it automatically generates the semi-landmark points along there. So if I turn these off, you can see that there's points on the surface where I place those big arrows. So it generates the points along that red curve, and then it snaps them to the surface. So the original point was semi-landmark point was generated on this red curve up here, and then it gets snapped to the surface so that the points lie on the surface. It's a key thing. You're trying to measure your specimen, not some strange mathematical function. So you want it to be projected back to the surface. Another cool thing you can do is change the density of the semi-landmark sampling. So if I go and select curves, I can select my curve. Let's zoom in so we can see it. So there's my curve there. The surface is turned off. I can turn the surface on so you can see it. And then I can change the density of this. So this is the number of landmarks across the whole curve. The numbers that are shown here are constructed such that you always have a point on the control points where you placed it. So it may seem like it's not very flexible in providing you certain numbers, but it's guaranteeing when you pick any of these values that you always get a point where you place these, and then it samples the same number of points in between these segments. So we have one segment here, 2, 3 segments in between the points that we placed. And so there's going to be the same number of points sampled between these. So this is the minimum. So the minimum is just no points, no semi-landmark points sampled between there. We just have our control points. And then this is one level up. So now we have one additional point in the middle, and so on. So that's where these values come from. So it guarantees that you have the same number of points within each segment. And then it projects those points down onto the surface. So depending upon the surface detail that you want, you can pick a bunch of points. We do put a maximum, because who would be crazy enough to use more points than that? That's a way to do that.
David, in regards to this, is there a way to flip the direction of the curve and actually change the ordering?
Yeah, you can do that too. So that's, it's this, yeah. So I have this one selected, and then you do this. So the reason you do that is it changes the order of the sequence of points when you're exporting. So if we do it in this direction, and then we look at the order of the points and how they're exported, that's what this is here. These are all the semi-landmark points that are being exported. From specimen to specimen, if you're just manually placing the points, it's easy often to put the points in the wrong order. So if you do that, this is a way to make sure that the primitives are ordered in the proper direction. If one of these semi-landmark points falls on, a hole, so if paleontologists are looking at some fossil and there's a whole piece that's broken off, excuse me, you can mark the individual points as missing. So in this case, you can see here, this little thing is allowing me to, walk through these semi-landmark points, and then I can mark that point as missing. If that makes sense. So missing would be the data literally is not there. And that's important when you're doing statistical analysis across these different things. Similarly with single points, if a particular point falls onto a piece of surface that is missing, you would mark that as missing. So there's still a representation of the point, but its actual coordinate doesn't have any meaning, if that makes sense. And so if you're doing generalized percussive analysis or something like that, you basically take that point out of that computation. Let's go back to here. Okay, this is fine. So that's curves. Then you can also do patches. So patches are, you know, a grid of points. So very similarly to curves. So I did shift left click to start it. And then you get these, there's 1, 2, 3, 4, 5 main points to start moving around. And so I can grab these and I can spread these out. So if I need to cover a large area, this is a good way to cover a large area. So hopefully you have some anatomic feature. You know, let's say we might be able to move this up here, and let's say we want this edge to follow this curve here. Turn this thing off. And maybe this edge, so down here. And then in this case, there's internal structures. So it's grabbing some of my points here. If you see that, so the surface is not laying on the surface that I want. So what I'm going to do is I'm going to bring this back, and I'm going to grab this point. I'm going to tell this point to stay on top here. Same thing with this guy. So I'm going to grab my middle point here. I'm going to tell it to stay on top of the surface. And then I should start keeping these guys up here a little better. And then there we can get a grid going across that surface. So it's a little more condensed on this side than on the other side. And then, you know, just like with the other things, you can change the density of that. Surface. And here we can do it in multiple directions. There's a high density grid through there. The surface area of this is computed here. It's in really small millimeters, so we can't see it. Change to say here. There you go. So this tells you the surface area of the patch itself, not specifically the surface underneath it, but it's computed from the patch. So as long as if this patch accurately represents your surface, then that's a way to measure some surface area. Let's see. There's also a joint primitive that can be placed on like condyle surfaces. So like the TMJ, it's mostly designed for the TMJ, but you should be able to place it on opposing joint surfaces, and it puts a surface on the condyle and then on the opposing surface, and it makes a matching two patches that match. So you can have point-to-point matching, say measure the gap between the joint. Doug, you're going to say something?
Yeah, we got a couple questions I think we should go back to. Regarding the curve where you change the order, it appears that even though we've changed the order, it's still ordered from, let's say, 5 to 9 when it's exported. Are we looking at this wrong?
This will change the ordering, so you might need to study the points. Let me get rid of some things. Let me get rid of the curve. Sorry, the patch. So these points again are these names have. I mean, I don't know. I can't remember if you can rename a particular point. Oh, yeah. So the automatically assigned names might be the issue here. So I'm going to name these ABCD. I'm let me get rid of these. Oh, no, that's fine. Okay, so I named each of these points A, B, C, D. And then if I look at the export, you should be a matching name in here. I'd be wrong. I thought the names would be in here. Maybe it's well, let me change the density down to something smaller. Export. So these are our single points. Here's our curve. Point 1, 2, 3, 4. Let's find some different values here. Okay, so this value here, so 399, and then the end of it is 381. So if I go back here, click this, flip it, go back to here, those should have changed. So now we have 399 down here at the end and 381. So that changed the order of these points for that curve. So it flipped the order of them and how they're exported. So it definitely did that. These guys very likely followed suit there. So hopefully that answers that specific question.
And now that you have this curve and set of semi-landmarks that you care about, is there a way to make a default like set of semi-landmarks for specific curves on multiple scans?
Yeah, you can do. You can set up templates to represent the set of points that you want, and place those onto your specimen. So let's say for this guy, let's say I wanted to do that. So let's say I did points. I wanted these 4 points here. Let me delete these and start over. So when setting up your template, you want to do it kind of in a particular way. I mean, you'll have to try it a few times. Delete all this stuff. Okay. So I'm going to create my template from this guy here. And you kind of want to cover, so the way the template works, there's a couple of different ways you can set up your template. You know, in the main principle is that you're just collecting a set of the landmark points that you want to put onto your specimen. And then another way to think of it is I want to put a minimum set onto my specimen and then have it sort of predict where all the others are going. So if you're doing hundreds of points, you might want to place just say 5 points and then have it predict where the other 95 points go. So a way to do that is you kind of want to cover the boundary extents of your specimen. So I'm going to put a point here, I'll put a point here, and a point here, and four minimum of 4 to 5 points is a good starting point. I'm going to put a point up here. It's not a great place to put a landmark point. It's kind of a featureless area, but nonetheless, I'll put one up there because I don't know anything about these shells. So now I've got 4 points. See how they're kind of in a plane? I don't necessarily want them to be in a plane. Kind of want them spread around on the surface, or kind of spread around on the extents of your object. Then for fun, let's put a curve here, and let's do another curve here. I'll continue that. So let's do that. And let's do another curve on this edge down here. So let's do curve like that. So what I'm going to do is I'm going to use those first 4 points as my anchor points. And then I'm going to have it automatically apply all of these other guys. So I'm going to create my template, new template, shells, and I'm going to pick my 4. So you can see I got my 4 points and I got my curves. If you name them, you'll be able to see the names here, which will make things a little bit easier. So I'm going to make my points, my anchor points, and then I'm going to make my curves things that are automatically placed over here. So that's what splits this up. If you leave things over here, they don't get added to the template. To the template. Yeah, you need at least 3 points to start the process, because what it ends up doing is it creates a thin plate spline warp to then warp the other points. And then save it. Chris Robinson asked another question, like how do you, if you have a missing point, how do you, or is there a way to predict where that missing point would be? This is a way to do that. So what you could do is you could take your point set, create a template, and then have it predict that missing point by excluding this, which I'll show you in a bit. Okay, so now I created the template from specimen C of the shell, so I'm going to go to specimen D. So I created the template from here, and then I'm going to go to specimen D here, this guy, and see if we can apply that template to this shell. So the way we do that, we go back to the template, go to our templates wizard. We got our shells template stored here, selected here, and I'm going to do the anchor points. And what that's going to do is it's going to require me to place those anchor points first onto my surface. So I click start. So it wants to know where point 1 is. Now, if you built your template properly, you gave these things names, and if you're a shell expert, you know what the names of the different points are. I am not a shell expert, so I don't know what they are. And I can't remember where I put the points. I think I put them, I think the next one is here. Next one is here. And the other one is like up here somewhere. So now that I place those 4 points, it automatically brings in the extras as these light blue colors. And it's using a thin plate spline warp to guesstimate where those should be. And so if I move any of my points around, it updates that thin plate spline warp and then moves the others. So now what I can do is I can grab these and I can adjust their positions. So I can say, oh no, it should be over here. And as every time you update a point, it updates that warp to make it more precise for that specimen. So I've got some curves there. And these guys are off in space. So to get these on the surface, so again, if I have it over here, I can't really move it onto a surface. So I'm going to rotate it so that the surface is behind it, so that when I click my point, it has a place to snap to. And there you go. Now I got my points on there. Now, lastly, let me show you one cool thing. Let's go to the, maybe not lastly, but next step here. So let me show you this warping thing. So here I can pick 2 of my surfaces. So now I have 2 homologous sets of landmark points on my C and D specimens. So I'm going to select C, select D, and then click OK. And that creates a warp between them. So now what it's doing is it's matching up those homologous sets and creating a thin plate spline warp between the 2 surfaces. And then you can move this little slider. And so this is, when you're 100% on this side, it's using the landmark point position from the A specimen. And if you move it over this way, it's warping it to the B specimen. So the more points you use across the surface, the better the warping will be. There's ways to export the surfaces. This would be useful, for example, if just you're a paleontologist, let's say, and you're analyzing a dinosaur and you're looking at vertebrae of the dinosaur, and you're missing 1 or 2 of them, but you've got the others on either side. So for example, you can take that vertebra, put a bunch of points on it on one side, and then take the other one on the other side. and then you can do a warp between them. And so if you know that there's a third vertebra in between those two, you can do a 50% warp between those two to create literally the shape of that missing vertebra. Or let's say there's two, then you could do the percentage for whatever the vertebra that are missing, and then you can get a pretty accurate representation of that as interpolated between those two missing vertebra. So that would be useful for a dinosaur or something like that, or a fossil of some kind, or in healthcare, human healthcare, the same kind of thing could be useful for a patient undergoing spine surgery. Let's say you're trying to make a 3D printed prosthetic to go into a damaged vertebra, spot. You could do the same kind of thing. Let me see if there's a couple other questions that were provided beforehand. So someone wanted to see some examples on human data, which we do have some scans. Something happened. Okay. So I think we're a bit out of time. I don't know if people want to hang around or ask questions, or but we should probably start wrapping this up. But whether you have human data or other specimen, you can kind of use it for anything you want. If you need to put points on things, this is a good tool to do that. So this is a cone beam CT scan, and you can do all the same things. That we just went through. Let's maybe stop there and see if people have more questions or ideas or anything. And hopefully this has been helpful for everybody. Maybe we'll do this more if people have more questions.
And if any more questions come along, please feel free to reach out at support@stratavan.com through the support channel on the website, and we will respond to them as soon as possible. But anybody who has to leave, do feel free to drop off, and we'll try to answer questions as they come in.
And we would also love to take the opportunity for future webinars. This is something we would like to do with some regularity. So if there's topics that take maybe more than 5 or 10 minutes to explain, but would be useful for a demo, or especially those of you working with larger groups that are tackling the same problem and could maybe use a webinar to demonstrate a common function that you guys are looking to use, whether it's with peers or students. Please reach out to us. We'd love to coordinate these in advance so we can be the most use to you all.
Yeah, Christy, you have a question about the R packages. So I think we would need to know more about what you want to see there. So if there's, yeah, I think we just need more information about that.
Yeah, I think your specific question about importing into like a geomorph format could be done easily, but creating something like a R package over checkpoint, we would need some more details. We would just need the specifics of what that format is. Another question, David, that did come up, when we go back to the meshes that you were looking at, there was a question about duplicates. Let me see.
Is that in the question chat?
Yeah, it does look like we tried to replicate this, but basically when you use the select combined points function, sometimes you get duplicates of some landmarks. Is there a way to not get the duplicates, or is there maybe some advice you can give on how to minimize the number of duplicates, or change the ordering or something?
Let's see. This one. That one. So is it specifically, so I gotta see the scenario. Like, are you doing some single points, you know, and then trying to do a curve or something between them? So it kind of depends on the situation. So in this case, I've got these single points here, and I've got this curve, and maybe I want the curve to now, you know, I want to effectively have it go between those 2 points. And so,
Just to clarify, this is when using a template, and it seems to only occur in the export, not necessarily in the view.
we'd have to see the circumstance. So if we can get a copy of the template, maybe some data and the specific circumstance that leads to that, then we can look into, you know, what's going on to better answer the question. Yeah. So I don't know. Please send an email. That'll be a little bit. If you can do an email, be like, this is kind of the thing that I'm doing for my data. This is a screenshot of how I set up my landmark points, and then I'm seeing this. You know, when it pops out, that'll be helpful. Most people are still on, I think. Let's just go all day. Let's just do this all day, a checkpoint day. No, I don't have enough
Yeah.
coffee.
David, can you show how you're switching between landmarks with hotkeys?
With hotkeys? I believe there is a, yeah, I'm not sure we made it through all the questions that came in. So I think so you can select a point and then holding down shift and then doing the arrow keys allows you to zip through all the points. You can see I'm holding down shift down here, and then I'm clicking the arrow keys as I go through these. So that's a way to do hotkeys. That was some request that someone had. You can click these things to change sort of the rendering. You want to be able to see the points on their own. This is surface transparency, slows things down though. So be careful. Making the points bigger and smaller. Are there any other questions that people have?
What other kind of different statistical analyses can you perform? For crusties, principal components, discriminant function?
So in the shape analysis tab, we have some basic support for some of that stuff. And so you can, so if you've got a group of specimen, you can create what we call a population. So you can create a population database effectively here, and then you can add specimen to that population. And so each specimen that you add to the population needs to have the exact same set of landmark points placed on them so that they're homologous. And then once you have that, you can then do some basic statistical stuff within the software. What people typically do is they just export the landmark points and then do stuff in R, or a lot of the other paleontology tools that exist to do those analyses outside. That definitely stretches my statistics capabilities and very much gets into you know, the background and training that the folks that use these tools know really well. So it's almost better to talk to some of our customers that use the software on how to do the analysis than us in particular. I don't know if that's a good answer to that question, but.
How about using checkpoint for landmarking that requires mirroring, like something like fluctuating asymmetry?
Did somebody ask that question, or are you?
Yes, somebody else does.
Or are you trying to make things hard for me? We use checkpoint for landmarking that requires mirroring. Can you, so Celine, can you provide more information on that? Like is it for like, I lost my mouse. Can't find my mouse. There it is. Okay. So in this case, you know, we have a symmetric. So are you trying to place, Celine, are you trying to place, so like we have bilateral symmetry in this case. Are you trying to place points on one side and you want to like snap them automatically to the other side or something like that? So I'm not sure exactly. So yes, something like that would be great. So it doesn't currently support that kind of capability. So again, it would be more helpful to understand like what are you trying to do? You know, the big picture of things. Like you've got 10,000 specimen and you only want to put the points on one side, and you want to automatically reflect to the other side or something like that. So is it like mathematically possible to do that? Yeah, we could, you know, do that. But it helps to understand, you know, the big picture of what you're trying to accomplish from your use of the software. If the challenge is, you know, just the monotony of placing a bunch of points, I would recommend using templates to create a template of all the points that you want to place. That can help speed things up for sure in terms of placement of points. Once you collect your points, if you want to do, you know, you can export the points and do some sort of, you know, symmetry analysis or something like that by doing reflection across the sagittal plane. There's lots of things you could do. Chris Robinson saying you can collect landmark points on one side and then on the other side, and then put them into separate files into the stats program, and then you can mirror the image. So hopefully that helps answer the question a bit. Usually what we end up doing is, you know, people that use the software are trying to, you know, accomplish some research project or task or something like that, and they just want to know best on, you know, how to use the software to get to the endpoint. What really helps us is trying to understand the bigger picture of what are you trying to accomplish, and then we can help navigate the steps in using the software to achieve that goal in an efficient manner, because placing landmark points can be extremely tedious, especially if you need to put hundreds or thousands of landmark points on, which many of our customers do have to do that at times. Are there any other questions? Still a fair number of people that are hanging around.
Well, I think this might be a good time to maybe start wrapping it up. For everybody, we're going to try to send out the recording as soon as we have one available. And then again, if you have any other feature requests or any other questions weren't answered today, please reach out on our support channels, support@stratavan.com, or through the website at the support tab. And thank you for joining us.
Yeah, thanks everybody very much. really appreciate everyone's time and participating, plus also providing the questions beforehand, because otherwise I had no idea what to do, and also providing some pretty awesome data to take a look at, like these shells. It's always fun to see how people are using the software and the things that people study. It's amazing to me what people study. So thank you everybody, and hope everybody has a great day.